going on in here? Oh, you guys draw cute pictures. It makes it really hard to erase things. Should I just like work around it?
Yeah.
All right. Okay, so I already yelled at my 306 class, but I'm gonna give you guys, so those of you that are in 306, you're gonna have to listen to it again for 2 minutes. I'm gonna yell at you guys for a second, but not about anything you did. I'm very quickly gonna say that if you're in math or you're in a quantitative field and you don't know how to program a computer, you really should learn how, because it's easier to get a job if you do and if you don't. So those of you that are math and physics majors in here, especially because those don't require a bunch of computer programming, you really should learn how to program a computer. It's going to make it much easier to go to a job fair and say, hey, look, I know it sucks. A lot of people don't like programming a computer. You really should learn. I'm going to be posting a guide on some places to get started if you're interested in doing that, right? If you got specific questions about how to get started in ways that go beyond your 101 class that's required, please let me know. Like, come talk to me about it. Second thing is, on the way into school today, I was behind a girl who was complaining about she got an A in a class, but her professor didn't know who she was and how anxiety-inducing it was to try to get a letter of recommendation out of this person. Didn't remember her. And doesn't he know that she got an A? The problem is, I personally give something on the order of like 100 to 150 A's every year. So if I gave you an A 3 years ago, it's extremely unlikely that if you never came to my office hours, because you didn't need to. I didn't ever go to office hours to meet the professor because I didn't have to. I didn't need it. The problem is that if I don't know who you are, it's very hard to write you a good letter of recommendation. If you don't need to come to office hours, that means you can come talk about something interesting. So I'm giving you an assignment, which is by the time you graduate, 3 of your professors should recognize you by face. Not by name, but by face. You don't have masks anymore, you can do that. Mostly, right? So when you get done, you're going to want 3 letters of recommendation. Make sure 3 people know who you are beyond just a canvas name that you know, like, oh, am I going to write a letter of recommendation? What can I say? They got a 94% in calculus 3. It's not a very good letter of recommendation. Get to know people. Okay, rant over. That I know that also, that's like for a lot of people, that's an awful thing to have to go through, right? To develop these relationships, but that's really going to bear out in a really useful way transition out of school and into either grad school or the work. Oh yeah, I know who you are. Okay, so I'm going to give you guys a, you know what, I was going to give you a choice, but I think the reason I changed my mind is because there was something I thought was trivial, but turned out not to be trivial. So somebody tell me what a TNB frame is. What is a TNB frame? What do I mean? Binomial uniroll. Okay, so you said unit tangent, unit normal, and what was the other one? Binomial. Okay, what do they do? These are the names. What are they? Ah, okay, so this is attached to, so the binomial vector attached to. This was associated with twist. The more mathematical way of saying this is torsion. But so that's what the binomial, you know, and this is related to dB. Change in the binormal tells you something about the way a path is twisting. What does change in n tell you? Direction of turn. What does t tell you? Direction. It's linear direction, right? Yeah, so linear direction. Now, the thing to know about these is they are just directions. They don't tell you anything about how fast anything is going, right? Yep.
So if I had like a little, if this was the little plane that I had was tracing the path,
yep.
This is the normal vector, then like changing the unit normal would make
yeah
that and the binormal.
That's right. Yeah, so the way to think about it is, you know, you might as well, you have 3 fingers, right? So you should get the whole, so the frame in the left hand, it's not left hand rule, it's the right hand rule, sorry. Left hand rule is something else. We'll deal with that later. The right hand rule, your index finger is going to be T, your middle finger is going to be N, and your thumb is going to be D. And you can keep track of the motions by just rotating that, right? The tangent vector tells you what direction you're headed. The normal vector tells you what direction you're turning, and together they dictate a plane a turn is happening in, right? As the normal vector changes in space, it tips the plane of the turn. We talked about the example on a track with a car, right? A banked turn on a track. You go into the turn flat, but as you go into that turn, it rotates. And so that turn is not on like a flat plane. It's a rotated turn, okay? And there's two things that happen there. As you rotate over, the binormal vector goes too. That's a twist in the track that picks up. The normal vector and the tangent vector make the plane of the turn. The binaural vector tells you what the twist that happened is. So change in the binaural indicates that a twist has happened in motion. Okay. Of course, now we have to get all this. We have to get all this stuff back into stuff we can actually do physics with. Unfortunately, sorry. I mean, physics is like physics, and engineers put up with physics. So we're going to put some notation in where I can glue all this stuff back together again with the notion of velocity and acceleration so we can recover the notion of force here. And that will complete our study of differential geometry, and we'll move on to talking about vector fields. So what we are studying, remember right now, is we are studying a path. So we're going to try to put all of this stuff, which describes a curve, back together again with the velocity that comes from a path to see if we can describe force. Okay, so remember that x takes some interval contained in the reals into R3 is what we mean by a path. And we're going to make some notation here. There's actually two assumptions that we need, and I want somebody to tell me what they mean. So we're going to assume that this is true, and we're going to assume that this is also true. After, you know, the guy that likes to bomb the whole thing. What do I mean here? Why do I need these? What do they represent? What does that mean? Velocity never stops, right? The particle never stops. The reason that you need the particle to never stop is because if we're thinking about that as a path, this is all supposed to be continuous math. And if something stops and then starts again, that can actually represent a corner or a constant chunk in the behavior of the function that we're looking at, right? I don't want corners, so I don't let velocity ever equal 0. That's actually justified by the fact that if it is equal to 0, I can always decompose it into pieces where that doesn't happen, okay? What does this mean? Velocity cross acceleration is never 0. It's supposed to be velocity. Velocity cross acceleration is never 0. What physical meaning could that have? Means you're always turning. You're never constantly straight, right? You're never constantly straight, so that because if you were ever constantly straight, you have no acceleration and then there's no normal vector, right? The frame falls apart. If it was ever the case that you were stuck in a constant straight path, this vector wouldn't exist and the frame disappears, right? So again, if you do end up in a situation where this vector gets very small, or you get these constant pieces of straight motion, I mean, that doesn't happen physically because you're never moving without being encumbered by force. But if you were, you could just ignore that part and then study the turning parts, okay? So these are natural physical assumptions. This is the assumption that you never stop. This is the assumption basically that you're always under the influence of some force. Okay, so now we're going to define, okay. You guys, have you seen this notation before? Okay. Everybody in here who's in the physical sciences or engineering has seen this probably, and everybody in here who has not is not. Maybe if only the physics majors have seen this. I'm not sure. What does S dot mean? Yes. This is basically standard notation in some fields, right? Okay. T is equal to B divided by the length of B. That's the definition of the unit tangent vector. And we remember, I don't know, like you guys remember that like ds dt was equal to the length of the velocity vector. So S dot is equal to the length of B.
So what does S dot represent here? Wait, what is this? Length of velocity is speed. Ah, that's a good question.
Remember that the way that we define S is equal to the integral from A to T of the length of x prime of tau. Tau. The fundamental theorem of calculus told us that ds dt is equal to the length of x prime of t,
But the length of the derivative of the path is the same as the length of the velocity vector. I know there's a lot of notation here, but all of this stuff kind of glues together. X is the path, its derivative, its velocity. I could also call that v. We defined this little length function in terms, remember this had a square root distance formula thing in it, which is just the length of this vector in derivatives. So essentially we're chaining all this stuff together now. S is a little length function. Its derivative is the length of the velocity vector.
Oh, yeah.
Right?
Right, but I thought in the note, you know, the curvature.
Uh-huh.
So I thought.
We're not doing curvature right now. We're not.
Right, but isn't the denominator?
Yeah. Oh yeah. I could put that right here if I wanted to. The length of the velocity
The
vector.
denominator has the length of the SDT, not just the SDT.
But I mean, the length of dsdt.
It has like the length.
Yeah, it's the absolute value, right? I know I put it down there. Like there's a notational artifact in the way that the book sets this up. Because this thing right here, this object, this function, is a scalar valued function that I have to measure its absolute value, right? We don't know prima facie that this thing is negative or positive, right?
Wait, so if you were to put the two, that's not absolute. I thought that's measuring the length.
When you take the length of a scalar, you're just taking absolute value.
Right, so isn't it supposed to be the length of the SDT, not the SDT itself? The absolute value of the SDT is equaling.
Hold on, I am absolutely lost in what you're asking me.
So isn't there supposed to be the two bars on the side of the SDT?
Here?
Yes.
No, this is just the derivative of this thing. The derivative of S with respect to t is that object right there with t plugged into it.
Then how come the curvature has?
Because the curvature formula, the way that the book presented the notation for the curvature formula falls out of the chain rule. So the chain rule applies more broadly than the specific case. It just turns out to be the case that the length of a vector is the same as the thing itself. There may be a misprint or I wrote it down wrong in my notes. The point is it doesn't matter. dsdt is a scalar value that represents the speed of the path that you're on. So if there's a mismatch in what I wrote, like adding more bars to this doesn't actually change it. The length of a number is just a number.
The SDT is a number?
Yes. The SDT is, I mean, this, as soon as you took the derivative of S and you get this out, lengths are always numbers. In fact, they're not just numbers, they're positive numbers, right? The length of a vector is always a positive scalar. So dsdt is a positive scalar. That's actually even why this makes sense to call this speed. The length of the velocity vector is speed. Okay. Okay. Completely lost my place. Okay, so what is the velocity then? I mean, that's the speed. Is there any way I can use these to reconstruct an expression for the velocity at time t? That tells you how fast you're going, not what direction you're going. This tells you what direction you're going, but not how fast you're going. So you can decompose this like this. Velocity is equal to a function that tracks how fast you're going and a function that tracks what direction you're headed in. Okay, this is just a notational thing, but this is an important decomposition, right? Velocity has two components, a magnitude and a direction. Okay? So that's our sort of our first big formula for this setup, is that v of t is equal to s dot speed times direction. All right, next. I mean, I don't want to compute anything. Where the hell am I? So confused. Okay, so let's take a look at, actually, so this is actually curious now. So it says that velocity is always parallel to the unit tangent vector. I mean, that makes sense. That's what unit tangent vector does. Yep.
So what's the purpose of that time?
Okay, so why are we using this? So this is this convention here when we're using these dot derivatives, we're basically indicating a time derivative. Like, so a lot of times when you're working with these systems in practice, there are spatial derivatives and time derivatives. These are time derivatives we're keeping track of. And the fact that we're using the dot here is indicating that this is also that we're dealing with a scalar quantity, right? And this is the notation of mechanics, basically. So if you study mechanics, this is one of the conventional notations of mechanics, is to work this way. Okay. I mean, part of it is because it's absolutely unambiguous what you mean by this. Whereas if you're in mathematics and you start piling these derivatives on top of each other, it just gets really messy to constantly, you're always taking derivatives. So why should I have to write by dt every single time I do it? So it's convention, and a convention of convenience. Okay, so now the question is, why would we do that? What is the point? What is the point of decomposing this function this way? It might seem artificial to do that, right? So who cares? I manipulated some symbols and then you went out of your way to define this new thing called s dot so you could write this function. Why do that? Well, what's the derivative? What is the derivative of velocity? Okay, so on this side, it's the acceleration vector. As a function, you take the derivative of velocity vector, you get the acceleration vector. What happens over here? Well, I've got two different functions of time multiplied together. So what am I going to do with it? Not the chain rule. That's one thing. Two functions multiplied, we don't use the chain rule, we use the product rule. Okay. So d by dt of s dot t plus s dot times d by dt dt. S dot dot, there we go. Yep, why not? The second derivative of s with respect to time times the unit tangent vector plus this guy right here, dt dt. What is this? What's the definition of curvature that we wrote down? Because man, this is starting to look an awful lot like maybe curvature is involved in some way, right? I mean, we've got this, the curvature was defined in terms of dt, wasn't it? I think we defined it that way, if I remember correctly. I mean, I did it.
Yeah.
So what was it?
So it's gonna be a normal time velocity.
Let's see. Curvature was equal to, let's not even go. This guy right here, dt ds, was equal to dt dt times ds dt. That's just the chain rule. Or I've got this backwards. This is dt dt is equal to dt ds ds dt. That's by the chain rule, right? I believe that was by the chain rule. Yeah. But isn't this what we have right there? Isn't this?
We wrote it down in terms of S. I think. Maybe not.
Oh, so ds dt squared. Right. Yeah.
I have the curvature of t is equal to d capital T over ds.
D capital T over ds. Yeah, because if you divide both sides by ds dt, you get this, right?
Right.
So what we're trying to do is we're trying to come up with a physically meaningful way of replacing this tangent vector with respect to time with something that's going to get us something in the frame, right? There was a relationship. Do you guys remember there was a relationship between the unit tangent and it's the derivative of the unit tangent and another vector in the frame? What was the relationship?
dt over the length of
dt over
the length
is equal to
the unit length.
That's interesting. How's curvature defined? The length of what?
The length of dt over dt.
Oh, so that's a K right there. This is a K,
No,
right?
because there's no ds dt in the bond.
All right. Let's put all this together and see if we can derive a meaningful thing. Here's the goal. I have dt. And what I want is something with an n attached to it. That's what I'm after. I want something multiplied by a normal vector over here because
N times the length of that.
n times the length of that's not an equation. You have to give me an equation. You guys are just saying terms, right? Is there some equation we have that relates these two things?
The length of that
Over.
or sorry, that's the denominator.
Man, I'm starting to think maybe I didn't do a very good job of organizing this when I taught it to you. Like,
I just switched up the order. That was the denominator. And the numerator was the capital.
okay, I'm gonna make an assertion. You guys tell me what's going on. So I'm gonna, you know what? I'm just gonna tell you. I thought I had this organized well enough in my notes that. So I'm gonna tell you now that the goal here. So why am I doing this? That maybe we should talk about why. Here's where we're stuck. We have a of t is equal to s dot t plus s dot times dt dt. What I'm thinking right now is that this is linear acceleration. This is acceleration I feel like moving in a straight line. Am I speeding up or slowing down in my straight line motion? This is acceleration I'm feeling with respect to the turn that I'm trapped in, right? This is radial acceleration because this is telling me something about how quickly I'm turning, right? So the speed with which I'm turning times my velocity, right? My speed times how quickly I'm turning is measuring something about how much acceleration I'm feeling on my turn, right? So if this thing is associated with the sort of radial or turning velocity, turning acceleration. So this is turning, this is not a technical term, turning acceleration. And this is linear acceleration. The idea is that my acceleration on path decomposes into two pieces. A piece that measures how I'm feeling motion changing forward and backward, and a piece that's pulling me into the turn that I'm on. Okay? And they're orthogonal to each other. This is in the direction of t, and my assertion is that this is in the direction of n. N tells me the direction I'm supposed to be turning, and I just need to get n multiplied by something that tells me the magnitude of the turn that I'm on. Okay? So maybe what I should do is just tell you what the answer is. This turns out to be equal to s dot t plus k s dot squared n. This is kappa. Okay. Why does that make any sense? Instead of like rooting our way through identities, I'm telling you, if you actually did the computation, you can write down what these things are all equal to, and you will recover that all of this together is equal to s dot dt. Why does it make sense that all this stuff is here? I mean, if this is radial acceleration, why does it make sense? What does each piece tell you? This tells you what direction you're turning. This tells you how sharp the turn is. Because remember, this just tells you, am I turning left or right? What direction is the plane of my turn in, but not how hard the turn is happening. This tells you the size of the circle that approximates your turn, direction of turn, tightness of turn, but even that's not enough to say what the force on you is. I also need to know how fast you're going. That's what this tells you. Maybe in the dim recesses of your memory, you've got the idea that radial acceleration is related to the square of your velocity or square of your speed. That's kind of what's going on here. Check.
I remember the couple of the length of so where's the n part of them?
There's a relationship between, if you actually go back in your notes, I should have written down somewhere that you had the relationship that, where did I actually write that? That n is defined to be, really the relationship in the background is that dt ds is equal to kappa times n. You're a unit, so basically the change that you have with respect to where you want the curve is equal to the curvature of the thing you're on in the direction n, right? So that this derivative actually does track how hard the turn is. And this was the piece
This was the piece I was hoping somebody would cough up, but since I taught you like 18 formulas last time, it's not surprising, right? So I should have actually given you this and asked where it came from instead, which is my bad. So is it clear why it's a, hopefully this is a post hoc justification, but the motivation for wanting to do this, the motivation for wanting to come up with this weird sort of artificial way of writing the velocity was so that we got this beautiful decomposition of acceleration into its linear component and its radial component, right? That at any point on one of these curves, you're being subject to two different accelerations. One corresponding to how you're moving in your straight line path. Are you speeding up or slowing down by pressing on the speedometer? And one corresponding to the velocity induced by how quickly you're turning the steering wheel. It's really what the analogy is here. Make sense? Hopefully. And if you haven't seen that before, the physical background here is, as you're traveling, you can imagine if you're not traveling with constant speed, at any given moment, there's a measure of how quickly I'm accelerating in this direction by pressing the gas pedal, and a measure of how quickly I'm accelerating in this way to turn myself along, right? Some force has to be exerted to turn me, right? Objects in motion tend to stay in motion. It's kind of a boil down of a much more complicated rule that says if you're on a linear path subject to no forces, you will continue on that linear path. So if you're going to be turned, you will be turned by a radial force. So there's a radial force. Let's not get mass into this yet. A radial acceleration and a linear acceleration. And the combinations of these things are why roller coasters are so nauseating, right? You're rolling down a hill really, really quickly on a roller coaster, and the first thing they do is snap you into a turn. Well, you go from feeling only this as you race downhill to all of a sudden feeling this and radial acceleration as you get slammed against the side of the car because you're being whipped into a turn, right? And both of these vector components are active in that case. And again, I'm only emphasizing this because everything about this formula is built up from stuff we did, but in a way that's supposed to tie in all of the ideas that we've studied, right? Curvature shows up. Is that right? Yep.
I'm just like writing it out. I'm just like a little confused because like in curvatures, like it's like the magnitudes, like the division of the two magnitudes. Then how do you get rid of the like magnitude of TS of the
Right here. The TDS is dt dt over the length of ds over length ds dt, right? So there's a you use the chain rule right here to get a dt dt and a ds dt, and then it all cancels out with that algebra.
Okay.
Okay. What are we missing now? All these beautiful accelerations, all kinds of crap going on. Just something that's not in the picture yet. Should we just ignore it? Nobody wants to see torsion. How is torsion defined? We have this tau, right? How did tau come into the picture? So this basically, at this point, we have all of the stuff set up for describing the forces that are, if we put mass into the picture, we get forces, right? That's the idea. We've got acceleration due to linear motion, acceleration due to turning, curvature is in this picture. Where the heck is torsion? What was torsion defined to be?
Chop. That would be how, where, dt minus tau.
Okay, this dude right here, this is the torsion. It's not necessary for the picture that we're building right here. So all together, we have all the different ways that you need to describe one of these paths. And then there's a really, really cool way of keeping track of it all. So here's everything we've got. We had S is, I know I wrote this last time, I'm gonna give you the whole picture now. S is the integral from A to T of the length of X prime of T, of X prime of tau d tau. We had in the intrinsic quantities, which are T, which is equal to X prime of T over the length of X prime of T. You know what a reasonable question to be right now would be? Are we really expected to remember all this? And the answer is no, you're not going to be expected to remember all this, right? So like you have to use it, but I don't actually care if you remember the entire corpus of differential geometry of paths. Okay. So the unit tangent vector was x prime over the length of x prime. We had n was equal to dt dt over the length of dt dt. We had b, which was t cross n. We have kappa, which is the length of dt ds, which is its theoretical basis, and the computational formula for it, which is the length of dt dt over ds dt. So yeah, you're right. I should not have put norms over this. This is just a scalar. It doesn't need to be there. And finally, we have the torsion formula, which is over here. It's whatever the number is that comes out of dt dt is equal to minus tau n. All those are intrinsic. Why are they intrinsic? Because they don't involve the particle at all. They only measure the path, the curve that it's traveling on, the roller coaster track. Then we had a brief argument that said that we can think of not intrinsic. So these are, I guess we would call them non-intrinsic. So these are particular to a path. And specific. It means how quickly I'm traveling. These things change when speed changes. V of t is equal to s dot t. A of t is equal to s double dot t plus kappa s dot squared n. There you go. It's the core of differential geometry. And what a lot of people use to keep track of this is a formula called the Frenet formula, which looks like this. Here, I'll give you here's something real fancy. Frenet, how do I know it's Frenet? I guess because he's French. I have no idea how to pronounce Serret, so I'm going to say Serret. It's probably Frenet Serret. This is fancy. It's a way of remembering all this. T prime, n prime, b prime is equal to 0, kappa, 0, minus kappa, 0, tau, 0, minus tau, 0, times t and b. This is a way that a lot of people use to keep track of what the basic formulas are. It's a system of differential equations, but it's a system of differential equations that tells you if you do this matrix multiplication, it's the multiplications that relate curvature and torsion to the frame and their derivatives. So it's a bookkeeping, device, basically. They're kind of cool. Now, what is a complication in everything that we've just done here? We're not going to actually do any more mathematics with this computation, but I want you to imagine that you're working with something like, but one thing that these frames get used for is controllers, right? Like a gyroscope for a drone, or an some sort of control device for a helicopter, or control device for really anything moving in space is in terms of these frames. So the problem is that I want you to think about is we've made a pretty big assumption in building up this frame, right? Which is that we're working in Euclidean space with respect to x, y, and z vectors. Have any of you guys actually worked with controllers? I'm curious, has anybody here worked with controllers on anything? Like three-dimensional controllers that report spatial information? So, like if you're working with a drone, well, if you're working with a drone, on the drone is a sensor that tells you the orientation of the drone itself, right? Like a gyroscope basically will tell you, here's where I am, and it reports it back to either a computer that, how does a drone stay stable? It's a good question.
Yeah,
Does anybody know how a drone stays stable?
it has like these. Someone mentioned it in the other class, but it has like a sensor where it detects like a certain angle, something like that.
Yeah, so living inside of a drone or any other thing like a helicopter that's on an autopilot system is a gyroscope. The gyroscope is not stabilizing. The gyroscope does stabilization, but it has to be spun in different ways to adjust for what the drone is doing, right? So inside the drone is a sensor that has a little frame inside of it that basically reads off, here's where I'm going. And it's going to report to some computer, hey, these are the forces that I feel. It's running this program in the background. But it doesn't necessarily have to do it in XYZ coordinates, was what the point I was going to make is. Part of the complication of all this is inside the drone is this sensor that is taking in information from gyroscopes and from GPS devices to try to tell you, like, this is how I think I'm oriented in space right now. Here's where I'm going this way, here's where I'm going this way, and I'll leave it up to you to take a cross product and figure out the torsion, right? It does that all in the machine. There's sensors that give this frame to you as a user. So oftentimes the frame that it's giving you is in some coordinate system that is not this coordinate system. This is an argument for learning some linear algebra. You've avoided linear algebra in your life because the way that you translate from XYZ coordinates into other coordinate systems usually runs through linear algebra. Okay. And if you've never worked in spherical coordinates, boy, oh boy, you've got some things to see. But yeah, this is actually what this is used for in practice. And if you guys ever do anything with robotics or automatic control, you're going to have to interface with systems like this. Yeah.
Why isn't XYZ?
Because so how are spherical coordinates defined, right? Spherical coordinates are defined with a radius from some center and then two angles. In a lot of cases, it's the angles that I care about, not necessarily like in a rigid 3D system like this, where I'm saying my motion with respect to X, Y, and Z. But if I have a rotational component, the way that I want to keep track of my motion is not in terms of linear motion, but in terms of radial, like tracking the angle of something. So those of you guys that have dealt, I actually know somebody, one of my best friends here was a mechanical engineer, and when he got to his first dynamics class, and he realized that he had to study rotating arms on rotating arms on rotating arms, that he doesn't want to be a mechanical engineer anymore, because the way that you do that is with these sort of epicycle angle trackers, and trying to translate that back into three-dimensional space as a function of X, Y, and Z is a nightmare. So yeah, there are some sort of anything that has a rotational component typically is modeled more naturally in spherical coordinates. So what does he become? A math major. He's department chair at Trinity University in San Antonio now. So yeah, he got out of mechanical engineering because it was too hard, I guess, or just didn't want to do dynamics and statics. The first time he had to solve a 10 by 10 matrix by hand, he's like, nope, not doing this. Okay. So I promise that when you guys have to deal with this stuff in practice, these problems are very difficult to write so you can solve them by hand. So you'll be dealing with a lot of helices. It's helices, you can do this very quickly on. Helices is the plural of helix. Those are defined very easily. So I'm going to give you guys some homework questions about this, where you're going to be studying things like x of t is equal to 2, 3 cosine t, 3 sine t. And the reason is because motion described on paths like this is very physically easy. Every turn essentially is flat. You wouldn't think that because there's this component here in the z, but I guess that's like a 2t. The idea is that it's motion like this. You get a constant circle that you're on. The curvature never changes on the way up. And this says something about the kind of acceleration you experience. Okay. So how are these things done in practice? Computers. Why should you learn how to use a computer? Because if you want to model this stuff, you have to use a computer to do it. Yep.
Isn't that like XYZ order? So you have to like horizontal.
Oh man. Man. You know what? You are correct. I should have written this like this. There. Now I have something that's spiraling up along the path, oriented correctly in space. You are correct. Might as well be accurate about it. This is moving linearly in the z coordinate is the idea. This is rotating you in the xy plane. This is pushing you up in the z coordinate. Thank you for the correction. Okay, so that basically completes our study of paths. And when you see this stuff in practice, and you will, if you're working in physics or you're working in engineering or you're working in any sort of applied mathematics, you do end up having to deal with the sort of motion of objects in three-dimensional space. So it's sort of classic mechanics. But a path is not the only sort of function of interest that shows up in physical applications. So we had x from an interval in R into R3 was a path Well, the other thing that shows up was is the idea of a vector field, force fields, electric fields, magnetic fields, right? These are things that are oriented in space. They don't just have a magnitude, they push things in directions, okay? So we're going to also study things called vector fields. This is what we're moving into. So out of paths which describe the motion of a particle and into functions that describe the force fields in which they move. So a vector field is a function f, which is a vector valued function that takes a domain in R3 and then spits out vectors in R3. So the way I want you to think about a vector field is, I guess technically R2 into R2 works too, but again, less interesting. F could also take R2 into R2. The point is the input space and the output space are the same size. And what a vector field does, I have lots of examples of this, so I'll pull the computer out again when I get a chance to sit down and do some demonstrations of this. In the same way that a scalar field was like a temperature map, a vector field is a flow map in some sense. A vector field takes every point and assigns it a vector. And if you took 241, you probably painstakingly drew these by hand, where you had to compute little derivatives and attach the arrows to the x and y coordinates, and then your teacher got mad if you didn't do enough dots, because they couldn't tell that you understood how the derivatives were changing. But the idea is a vector field assigns a vector at every input. And this is really the only reasonable way that we have of understanding this, because unless you can see 3 input dimensions and 3 output dimensions, so a surface in R6, you're not going to be able to visualize what the graph of this looks like. Basically, the only tool we have for understanding what a vector field does is to think about it as a function that takes in a vector and outputs a vector, or that it takes in a point and assigns it a vector. Okay. What are they used for? Oh. What sort of things are vector quantities? Electric fields. Gotta be careful. Fields, not potentials. Electric fields. Anything else? Yeah, you could have a velocity. Yeah. So like if you had a vector field that was velocities, that's the core idea of fluid mechanics. Ooh. Velocities, especially of liquids. Not liquids, fluids. Man, there's a nightmare class if you haven't taken that one yet. Oh, that's some burly math in there. Right. So the way that you describe the way a fluid moves is you basically describe locally how fast that fluid is moving. Right. And so a vector field is a way of saying this mass of stuff is moving in this way at this time. So you describe the motion of fluid through a pipe. I give you a function that describes what the velocity vectors of that fluid are at every point inside the pipe. And then you got to solve some gnarly equations to figure out what's going on. Anything else? I'll give you a really easy one. Gravity. Anything else? Sure. So basically the invention of the theory of vector fields was meant to address the interaction between, or was meant to study these things, right? The quantities that show up in physical applications that are vector valued. Now, of course, mathematicians took all this stuff and said, oh, let's look at all of them instead. I mean, who cares about the ones that are physically motivated? Let's just study all the functions because, we're dorks. And if we can study more things, we'll study more things, and the physicists can work out what's real and what isn't. But the idea is that there's some things we might want to measure about the way these functions act. And I don't actually know who covers this in 241. So if I mention gradient, divergence, and curl, are those quantities that people have seen before? I mean, I'm going to do it from scratch. I'm doing it from the bottom. We talked about gradient already, right? Talked about gradient. We talked about divergence. Let's ever talk about divergence. Talk about curl. Okay, so these things come up. Yeah, div, grad, curl. That's the sort of order. There's even a book called Div, Grad, Curl, and all that jazz, or something like that. It's one of the recommended texts for this class. I thought that was a little lazy. It's not really written in a rigorous way. The idea is that when I'm studying a vector, like a vector field like this, there's a lot of things that I might want to describe, right? If I put a particle down in a river that was moving like this, it would trace out a path, right? There would be a path that showed up like, oh, if this was velocities, this basically is telling you if I put a particle right here, it would have to follow the velocity lines. And it gives you the path that a particle would follow. If I put a particle here, here's the path that it follows. Other things that you might care about. If this was a fluid, you might care about the amount of fluid that's coming into or leaving a particular piece of space, right? And that has something to do with So what divergence measures is the amount of a field that's leaving some sort of unit space. You get this with electric and magnetic fields as well. And then there's also components of rotation as well. A vector field, if we imagine as a fluid, really the analogy that gets used here most often is we think of these things as fluids, right? If you have water that's being mixed up or just flowing in a river, it has velocities attached to it, but there's also things that we might care about. You know what an eddy is? It's like a little whirlpool. So there's places where the water might be rotating around itself. And there's a measure of that rotation, which is what we mean by curl. So the three quantities that we want to measure about these things are which directions is the velocity point and how quickly, how much of the stuff that we're measuring is moving in and out of a particular point, and how much rotation is happening. Those three ideas applied to generic sort of vector value functions turn out to measure physical quantities that we really care about. Okay. So again, this is going to be another study where we're going to attach the mathematical ideas of studying these functions to the physical quantity. Really, again, the analogy here, as dumb as it is, like the motion of water gets used all the time, which is sort of artificial because water is incompressible, but we use it anyway. But again, as the cheap analogy, imagine here that what this is telling you is you have some fluid and these are the directions things are flowing. Okay. Make sense so far? Oh, we only have 3 minutes left, so I can't tell you what a potential function is or a gradient field yet. But if you guys want to read ahead a little bit, one thing to look at would be this introduction to this, I think, is slightly technical, but not too bad. What it's going to do is it's going to attach the idea of the gradient vector. It's going to attach the idea of the gradients to the idea of detecting where this thing is moving. And it's also going to give you a very natural way of thinking about if you had some scalar field like a temperature map and you took the gradient of that temperature map, it would tell you the direction that heat was flowing, for example. Or if this was a picture of a mountain and you took the gradient on all the level curves, what are you going to get out? You're going to get a vector field that describes how water flows on that surface, right? So the easiest way to get a vector field is to take a scalar function and take the gradient everywhere. That's the very first thing we're going to talk about is how scalar fields turn into vector fields if you apply the gradient operation to them. So gradient of a scalar function is a vector field that describes, for example, the motion of water or fluid down some sort of, the fancy way is it describes motion against potential, right? It's the gradient across potential. Anyway, so I'll be more specific about that next time. Hopefully this is enough of a setup to motivate why we care about this, and we'll be more concrete. Thanks for putting up with me blathering. There is a new homework